Hello everyone, I'm Aida Rahmattalabi, and today I will present our work on designing resource allocation policies using observational data. And I will study this problem specifically in the context of housing allocation among those experiencing homelessness. This problem is motivated by the growing rate of homelessness in the US. According to a recent report by the Department of Housing and Urban Development, more than 580,000 people experience homelessness on any given night, making homelessness one of the most critical public health problems in the US. To address homelessness, housing interventions are widely considered as a key solution. There are two main types of housing: permanent supportive housing, that are long-term housing resources, and rapid rehousing, which are designed to provide temporary housing assistance. Since these resources are limited, service providers often use risk scores to prioritize individuals based on their vulnerability to homelessness. VSPADAT is one of the most commonly used tools that assesses one's vulnerability based on a variety of factors such as history of homelessness, mental health, or substance abuse. It is a self-reported survey which assigns a risk score between 0 to 17 to each individual based on their responses. In this figure, we can see the status quo policy for allocating the resources based on the VSPADAT risk score, according to which individuals with a score 8 and above are eligible for PSH. Those that are in the 4 to 7 score range are eligible for rapid rehousing or RH, and those who score 3 and below will be only eligible for basic services, which are referred to as SO. Upon arrival to the system, an individual will be assigned to either of these queues, where they wait to be matched to the appropriate resource. This policy is interpretable by design. In other words, it's easy to explain why an allocation is made. It also aims to be fair by prioritizing those that are the most vulnerable. However, there are several issues with this policy. First, the cut scores are not really tied to the treatment effect of the interventions or the relative arrival rate of the individuals and resources, and this can lead to a poor policy performance. For example, it is not clear whether assigning mid-scoring individuals to RH will indeed guarantee a high chance of becoming stably housed. Additionally, there may not be enough RH resources to satisfy the needs of all individuals in that score group, and this can result in long wait times. Finally, the current system suffers from a significant racial disparity in homelessness that disproportionately affect minorities such as Black people. More formally, in order for a policy to be implementable and effective, it must be evaluated and optimized simultaneously along different dimensions. One of the key objectives that we consider in this work is to ensure our interventions indeed help individuals exit homelessness safely. Housing interventions, however, have heterogeneous effects on different individuals. Therefore, an effective policy needs to take this heterogeneity into account and match people with the right type of resources. On the other hand, there are huge racial disparities, as I mentioned, in the current state of homelessness, and this disproportionately affects those from minority groups. For example, African Americans represent 30% of the general population, but account for 39% of the homeless population. Therefore, it is crucial to design policies that are aware of these disparities and are able to correct for them. Finally, prolonged homelessness increases the chances of being exposed to violence, substance use, or diseases, and therefore it is important to help these individuals leave homelessness as soon as possible. To sum it up, our goal in this project is to design a more efficient and equitable policy for allocating housing resources to those experiencing homelessness. For this, we use historical data available in the Homeless Management Information System, or HMIS. This data contains information on the historical allocation of resources, as well as individuals' characteristics such as risk score and demographic information. The data is observational, which means that those who have received a certain resource are systematically different from those who have not received any resources. So we cannot simply compare the two groups to estimate the treatment effect, as it leads to biased estimates. Now let's discuss the mathematical model of this problem. We model this problem as a multi-class, multi-server queuing system, where a set of R resources serve a finite set of queues. Similar to the status quo policy, the queues may correspond to grouping of individuals into low, medium, or high risk categories. But of course, we can consider a high number of queues. Both individuals and resources arrive stochastically over time. Each individual is characterized by a feature vector X and a vector of potential outcomes YR, which represents the outcome under that resource. In our setting, we consider successful exit from homelessness as a positive outcome. Upon arrival, individuals are assigned to a queue based on their feature vector. We use P to denote the function that maps feature vector X to a queue, and we refer to it as a partitioning function. Note that this function is not known a priori, and I will describe how we can construct P by grouping individuals who have similar treatment effect shortly. Arriving resources are assigned in a first-come, first-served fashion, subject to a matching topology M, which is essentially a binary matrix that encodes the resource types that serve each queue. Our goal is to design an optimal topology such that the value of the resulting policy is maximized. Here, tau is the conditional average treatment effect for each queue resource pair. And mathematically, it is defined as the difference between the outcomes under housing resource R and service only, which we consider as the baseline intervention. F is also the steady state flow, which depends on the matching topology. Set calligraphic M is the set of feasible matching topologies. It includes a set of constraints that enforce steady state flow for any matching topology M, as well as constraints that impose minimum average wait time, which we borrow from queuing theory literature. Adopting the maxi-mean fairness notion, we further augment this formulation with fairness constraints that enforce a minimum policy value across all groups. Now, in order to solve this problem, note that we need to specify both the partitioning function and the conditional average treatment effects, or tau QR. We employ techniques from causal inference literature, and in particular, causal trees specify both simultaneously. Causal trees allow us to estimate heterogeneous average treatment effect in the presence of selection bias. Similar to decision trees, causal trees recursively partition the feature space. However, instead of making a prediction at each leaf, they estimate the conditional average treatment effect. Since we have more than one housing resource, we construct a separate tree for each housing type. In other words, one tree for PSH and one tree for RRH. Now we can view the collection of these causal trees as our partitioning function, and we define queues based on the joint leaf nodes that individuals belong to across all trees. With this approach, we are able to construct the queues and simultaneously obtain the tau values to optimize the policies. Now I would like to share some numerical results. We use the HMIS data of homeless youth from 2015 to 2017, and we constructed a binary outcome based on the trajectory of each individual. For example, we looked at whether or not the individual has exited homelessness and what their subsequent destinations have been. We then use the causal trees to estimate the heterogeneous average treatment effect for both PSH and RRH across this risk score, which you can see in the figure on the right. As seen, PSH consistently exhibits a higher treatment effect than RRH, indicating that it is indeed a more effective resource. Further, the treatment effect of both resources increased with score, which suggests that higher scored individuals benefit more from both of these resources. Next, we see the policy optimization results across different approaches. As baselines, we simulate both a fully first-come, first-served policy and a status quo policy, which I refer to as SQ. We also compare with the deployed policy as we observe in the data, which is shown here under SQ data. Finally, opt and opt-fair are our approach without and with fairness constraints. According to this table, opt and opt-fair both outperform the baseline policies. Perhaps surprisingly, SQ performs worse than the first-come, first-served policy, but this is indeed due to the fact that how those cut scores are designed. Recall that according to the SQ, individuals with a score 4 to 7 are matched to RRH. However, as we observed from the data, the RRH treatment effect is highest for those who score above 7. Compared to SQ data, our policy values are competitive. We also improved the wait time over SQ and SQ data by 21% and 9% respectively. And we also obtain values that are similar to first-come, first-served policy. Essentially, we achieve the minimum wait time possible. And finally, we observe that opt and opt-fair have relatively similar policy values, which indicates that imposing fairness constraints results in a small cost in the overall policy value. The next figure shows the policy optimization results across different approaches broken down by race. First, we observe that even though under first-come, first-served policy, everyone has the same probability of receiving any of the resource types, this policy doesn't necessarily result in fairness in outcomes. Especially, we see that under this policy, Black individuals are significantly disadvantaged. SQ also yields a relatively low performance across all groups, which is mainly due to its poor performance overall. SQ data has relatively better performance. However, there's still a significant gap between the performance of Black and other groups and whites. On the other hand, by explicitly imposing fairness constraints, opt-fair significantly improves the performance for the Black and other groups. Finally, let's take a look at the diagram of the actual matching system corresponding to opt-fair. Here we can see that individuals are divided into 4 different score groups. Those who score below 6, individuals who score 6, individuals who score 7 and 8, and finally those who score above 8. Queues are constructed based on score group and race jointly. Solid lines indicate that a resource is connected to the entire score group or a collection of queues. The dotted line indicates the connection to a single queue within the score group. For example, in this figure, SO is only connected to the individual with a score 6 and race white. According to this figure, PSH is matched to all individuals with scores above 8, as well as mid-scoring Black individuals. RRH is connected to every individual in the mid-score range. As you can see, our modeling strategy uses the protected characteristics in order to ensure fairness. This is mainly motivated by discussions with the project's community advisory board, who suggested that in order to create a fair housing allocation system, there ought to be special accommodations for historically disadvantaged people. However, our approach allows us to construct queues that do not differentiate between people according to the race or any other sensitive attribute. And this is possible by imposing constraints that ensure topology has the same connections to all protected groups within a score group. In this figure, we can see the resulting matching topology after we add these additional constraints. And as you can see, race no longer appears explicitly in the construction of queues. I note that as a result of these additional constraints, however, we might lose a little bit on the efficiency, here about 4%. However, we're still outperforming both SQ and SQ data. With this, I would like to conclude my talk. Thank you so much for listening. I'm happy to take any questions.